And now the example for convolution of three function is the next example. Again, it would not be exactly the same form, but we need to do some. Let's keep the definition, otherwise we forget about. Oh, I already erased. That doesn't matter. We can look back at the text. Right. Because again, the rule. I mean, what the procedure is. You write down. You have an expression that you know. You want to compare with a convolution definition. You just want to manipulate your expression so that it's going back to the definition. So the express this is. Okay. And the expression is just, this is like a electrostatic potential. Right? Integrating over two volume elements, dq alpine, dq alpha double prime, rho alpine, rho alpha double prime. They consider these rows are the charge density. And the Coulomb potential between them, just the charge multiplied by the volume is, I mean, charge density multiplied by volume is charge. So multiplied by two charge and divided by the distance. It's electrostatic potential is the Coulomb potential. Integrating over all space, the electrostatic potential energy of the system. Actually, your text will indicate a different rows of one, rows of two. That could be a different charge density between two charge density. So presumably the two charge densities are separate into two distinct locations. Anyway, so this example is to convert that to integration in the Fourier space. And again, you can always just do standard Fourier transform of all the factors. So rows of two and this factor individually you do Fourier transform, and then finally you do some simplification, you get the final formula. But because we already have the 3D convolution, we can also put that in the standard form of the convolution and then use the formula that we just wrote down. So the idea is that this is similar to a convolution, not exactly the same. You can compare that to the formula that we just erased. You can write it down. So, no, the 3D convolution, and with other than the factor in front is the R double prime between C function is F double prime F R prime D R double prime minus R prime and H R minus R double prime. Right. And comparing this with that, and the first thing you notice is that there's no R. There's an R. So this is a function. Obviously, this becomes just a value. This is after you do the integration, it gives you just a value. Or you can say this is a convolution evaluate at a specific R. So, that makes it even easier. Now you compare with the form. So you have obviously you have alpine, your alpine, so you can identify rows of one as your L. If this is your L, right? And Then you have R prime. G is depends on R prime minus R double prime minus R prime. We get this one. We get this one as so the one over this distance is your G. So this one with the I mean in the denominator is G, right? Now again this is the same situation. Now this is depends on R double prime. This is defined as a negative R double prime. So we need to define as so this is, or you can say this is H, but with the minus R, H minus R double prime, right? Because I mean that this is positive, this is negative. So just like what we did in the last example, you need to redefine the function and then change the argument to this negative. Um, that's all it is. And then evaluate at r equals 0. Right? So finally, evaluate. So this become a convolution, evaluate r equals 0. Other than the factor of obviously the convolution originally have a factor 1. For 3D is 1 over 2 pi 3 half. But in order to apply the formula, you don't get this. I mean, if the position of these are different, you multiply it to the other side. So let's write down the formula. So the formula is this one equals to 2 pi we have, and then integrate all the Fourier transform. Okay. E to the minus I. This is the formula. Now apply this is the formula that we cite. Now applying back to this voltage or the potential energy. Now equals to just using this formula, you get 2 pi we have. And the Fourier transform F is just the Fourier transform of those one. This one depends on K. Now the capital G is the Fourier transform of this 1 over the but this is already a function, so this is 1 over G. 1 over Fourier transform. Because you compare the function with the function. This function is G function, but the function has argument R double prime minus R prime. This has R double prime R minus R prime. So this function is the Fourier transform. Transform the capital G is Fourier transform 1 over R. Okay. And now the last part H is now because of this minus sign. So just like what we did before, now we can go faster in the argument. It's just 5, 2, we transform but change K combination. And then finally this is e to the minus K dot R. But then we already chosen R equals to this, R equals to 0. So this is just 1. Okay, so that should be just the formula. Yeah, this is just 20.9. Except other than the 1 over T, 1 over R transform, which we already wrote down in the example. We have just we did that. This is a 3D 1 over R. Oh no, I did that. We didn't do that, but we did that in another example with the 3D transform. This is what it is. This is we did that in 20.42. The 1 over 2 pi. We have 4 pi. Okay, if you substitute this into that, you cancel this factor and you get a 4 pi factor in front. And you have Fourier transform rho sub 1, Fourier transform rho sub 2, evaluate negative k and divided by k squared. So that is 20/19. And that is the final form, obviously, without knowing what's rho sub 1, rho sub 2. You don't, that's the final form you can get. You need the specific form of the charge density to calculate that. But this is just transforming from the integration in physical space to the integration in the Fourier space. It doesn't matter, depends on which one is easier to use. One thing is that this is a double integration. This is just integrating just single volume of K. If you know the transform or the rows of 1, rows of 2. If you already know the transform, then maybe this one is easier, or maybe numerically easier because it just involves one single integration. This involves two integration. Okay, so now.
So then for the R that's in the G transform, is that a different R than the one you said?
This one, this R.
Yeah.
This is.
It's just a different.
This is the argument of the function. This is just calculating the Fourier transform of this function. We haven't evaluated anything. This is the function of g. This R is in the h function. This is in the g function. We have normally the definition of the convolution has this R minus R prime. So we need to write down in the same way like that, but because this argument only have R double prime without an R, so when you go to the h function, you only have a minus R, right? And then we don't have the R. So basically, we're saying that we can choose R equals 0 for this function. And for this R is the g function. It's the argument of the g function because by this comparison with the definition, g function, the argument will go into this factor. So this is the argument of g, right? So this is the argument of g. And the capital G is the Fourier transform of G with using this argument, which is just 1 over R, right? And we get to the K function of K, right? Just use this Fourier transform of this function, you get it. Is that okay?
Yeah.
Yeah. This is just symbolically, whatever. This is just to show that we want to calculate a Fourier transform of this function. But after you do the Fourier transform, it's a function of K. There's no R in here. Okay? Is that your question?
Yeah, I get it. But
Yeah.
now we have it, so we have like, so we can, well, the equation is going to kill the other constant inside, and then the rows just integrate that.
No, I already said that you cannot proceed without knowing exactly what the function rows of 1 and rows of 2. Those are arbitrary charge density distribution that can be any function, right? And this is just saying that the original expression in the integration in physical space can be expressed in the integration in Fourier space. One difference is that in the physical space that involves a double integration. You need to integrate 2 times, 2 volume integration. And that, I mean, analytically may be easy for some situation, but numerically obviously will be more involved because you now need to integrate it over volume 2 times, right? And that's a lot of more computational work. So if you transform to an integration in K space, in the Fourier space, that involves just 1 volume integration, the wave number space. That's a saving. In principle, but I mean, depends on what those functions are and whether it's easy to calculate this rows of 1, rows of 2. That's another story. So if for some question, maybe this form of the charge density is easy to calculate. It's easier to find the Fourier transform, then that is a good method to do. If you cannot get the Fourier transform easily, then each Fourier transform is a 3D integration, right? So you have a 3D integration to get the Fourier transform, and then another 3D integration. So that becomes no saving. right? So originally it's a double volume integration. Now you go back to a double volume integration. So there's no saving at all. It depends on the problem whether it's good to use that. Yeah. Yeah, this is yeah, the origin is rows of two functions, right? And this our double prime, this is our double prime. Yeah, this is double prime. Is it too small for you back there? It's double prime. Is you can't see it well back there. You can see okay. It's a double prime, maybe too small. Right? Okay. But, uh, what else? 4 minutes left. Yeah. Yeah. R double prime minus alpha. Yeah. This is the argument. This is the argument of the G function. You have a G function, you evaluate that at using the argument R double prime minus R. So the function is CR, right? The function is GR. And you evaluate that as, you identify this as a function of G using the argument R double prime minus R because we define the G, like compare this with that is one of the magnitude of this argument, which is the radial coordinate anyway. So this is the G function. But now we evaluate this G function at this argument, specific argument, R double prime minus R prime. So this go into here, which is just this one. It's okay. So the function itself is this one. So to calculate Fourier transform, we use this function. So basically, we do a Fourier transform 1/r. Okay, that's how the definition is used. Right? Is that okay? Do you get it? So we are not Fourier transforming over this one. We Fourier transform over the function because this is just the function evaluated at this argument. It's going into R in this function. No, this is by defining. We define a function gr so that when you evaluate this function at r double prime minus r is this factor. So this integral becomes f times f convolution between f, g, and h. This is just again. This is the form how you define a convolution, right? And this is the expression given to you. You just want to compare this expression with the standard form of your definition. And the definition call for you have three functions f, t, and h, right? And evaluate different argument. For the f function, this r prime. For the g function, evaluate r double prime minus r prime, right? So the function is defined like that, so that when you evaluate this function at this argument, that gives you this one, right? You get it now? This is just to compare the form of these two, and so that they are the same, and that require that you define a function G like that. And the formula also shows that the right hand side given by this product of Fourier transform, but this capital G is the Fourier transform of this G, this little g with this argument. Oh. And so that when you calculate the Fourier transform, you calculate 1/r Fourier transform 1/r. Okay, that gives you this result. It's okay. It's sometimes in this kind of thing can be confusing, but you just uh, think about it a little bit more. Try to convince yourself that's the correct way to do it. Right?